uniform and fine strings connection.
Well, thank you, Milton. Thank you very much, really, for the invitation. You, Ines, Pablo, the organizers. Well, the people here listening to this for the will. So basically, I'm gonna tell you a bit about, just the main result of the works that we have been doing for the last couple of years here in Utrecht. So basically, a compendium of 3 papers and the most important results that we got. So in essence, in some way, probably it's not the only way that we can see this work, but in some ways, a relationship between 3 random models, which are the 3 that we have over here. Most likely, most people here might be familiar with the UST, but not necessarily with the other 2. So no worries, because I will give a brief recap about them. But in principle, basically what we will do is to introduce each of these models and play around with them and sort of juggle between the results and say, hey, hold on, I have this relationship and this other one. So if we can join these 2, then I can relate these 2 models and calculate one thing by using the other one. So basically, it's just a sharing of properties between these 3 models in a very interesting way. So let's first begin by defining what the ASM is, Abelian sandpile model. So it's very easy to define. It's a dynamical system, which has a very straightforward algorithm. You just take a finite set in a grid, and you start to put some particles, So the amount of S is going to be a counting function, counting basically how many particles or the mass they have in each side. So basically, I will iterate as follows. I will choose one point randomly, uniformly at random, and I will basically add a particle, right? So S becomes S plus 1. Now, whenever at the beginning nothing will happen, but at some point it will happen that S will surpass 2D. So think, for example, in D equals to 2, you have basically 2D is equal to 4. So basically, whenever I have 5 or more, this point will topple because it becomes unstable. This is sort of like the reason why we call it the sandpile, because it's like thinking about the slope of a sandpile, and at some point it becomes unstable and it topples. So whenever it topples, what it does is it gives, basically it loses 2D of mass, and it gives 1 to each of their neighbors, right? So basically, this is what I do here. And if I'm at the border, I do nothing. So basically, I lose that mass. And then it might happen that now that point X lost some mass, basically, and it passes it to one of the neighbors, and that neighbor now becomes unstable. So this can keep on going and going. And eventually, since I have the possibility of losing the mass in the border, eventually I will stop. And then I will repeat. Choose one point at random, add 1 grain of sand, and repeat this toppling process. So why is this system important? Well, because, I mean, I won't go through all the details of the many characteristics that this has, but mainly because it was the first system to be devised that exhibits self-organized criticality. So basically criticality in the sense of, correlation lengths going to infinity and so on, but self-organized because it doesn't depend on any tuning of any parameter here. So there's no parameter to tune, unlike, for example, the easy model. So that's why it's important. Now I'm gonna say one phrase that for some very few people might tell you something, and some others it won't. So in case it doesn't tell you anything, just please ignore this. But it might be interested in knowing that there is a conjecture in which basically this system, in some particular scaling limit, converges to a logarithmic conformal field theory with some particular center charge and so on. Might be completely nonsense for some of you, so it's not important for you to understand this right now, but some people might be interested in knowing this. And this is also like one of the motivations why we actually started as well to study this. But for our work, this won't be absolutely necessary. Yes.
Alan, this conjecture is in any dimension or in
No,
dimension
two. Sorry, two.
Okay.
Yeah, very, very important. Yes. Sorry about that. Two. So in particular, there's only one field that when observable, that we will be interested in from the ASM. Yeah, whenever we talk about the ASM, we will actually be talking about the height one field. And its definition is super straightforward. Basically, it is just taking the indicator of the mass being equal to 1. Remember that since we topple whenever S is larger strictly than 2D, I will never, like at some point, I will have added at least 1 grain of sand to each point, and I will never be toppling. Basically, I will never have less than mass 1. Yeah, so I can have mass 1 or more than that. So 1 is the minimum. And this field is on 1 whenever the mass is 1, and 0 whenever the mass is larger than 1. Only that. And I should mention that this, at some point, if I keep iterating this process, I will, this is a sort of a Markov change in which I will attain the stationary, this becomes a stationary, basically. And this is the regime in which I am interested in this case. So yeah, this is the field I will be looking to. Just a rewriting of the algorithm in a more compact way. And why do I do this? Because this matrix will show up eventually further down the line. So if you remember, the graph Laplacian is defined in this way. Yeah, so the unnormalized one in this case. And if you look at how the algorithm went before, I can just write the toppling process as this update. Basically, the mass S becomes S plus the Laplacian. So this only for you to let you know that this Laplacian already is entering the game, and you will see it later on. So far so good. Nothing. I'm just defining how this system works. And then we will, well, I will not, but Durham did back in 2009, calculate the joint moments. And for that, just a brief recap. Whenever I have a set of random variables, X, the joint moments or the joint cumulants are pretty much like given, if I have the complete set of ones, then it's completely equivalent to having the other ones, right? And because they are related by this relationship over here. So only for you to remember, that is a matter of permutations, just a sum of products of them. So we'll eventually, like at some point, give the joint moments or the joint cumulants, which is like pretty much giving the same information, right? It's out of convenience which one we will write. So basically, okay. Back then in 2009, he gave this result over here, which it might seem a bit scary at the beginning, and I'm not interested in you to understand every single symbol here, which is nothing crazy, to be honest, it's just notation. But basically, I want to show a little bit the structure that we see here. So what he calculated is, first of all, the cumulants rescaled by some parameter of what? Well, of the height one field, recentered. So these two, the columns are just a recentering. So it's only H minus the expectation. Yeah, nothing else. Why the 2 dots? Well, because it's suggestive of some techniques that we might then use, but just imagine that this is only a recentering. And we need that because otherwise everything blows up. So basically he studied a scaling limit of the cumulants. Well, what scaling limit? Well, basically the set in which we are working right now is this one over here. So we will take U, just a regular well-defined domain, and we'll define the blow up and discretization of U by blowing U up and intersecting it with Z2. So far, everything is working only on Z2. Basically, all his results are in 2 dimensions, not D in general. So I just blow U up and then intersect in the square grid. And basically those are that's the domain. So basically whenever epsilon goes to 0, this converges to the whole Z2, and this is the limit that we're taking here. So what we see is that these cumulants, properly rescaled, converge to something highly non-trivial. These are sums over directions of derivation. Never mind that these are cyclic permutations, but the important thing is that everything depends on sums and products of double gradients of the Green's function in U, in the set U, right? So yeah, a perfectly well-defined expression. And in particular, we have a minus over here, which, okay, so far so good. Some of you might have noticed that this is actually an almost determinant, but it's not quite. It's a sum of determinants, but those determinants are related to each other. So maybe I'm getting ahead of myself, but this won't be a completely determinantal process, although it's kind of similar to one, but it's technically not. So far so good. Yeah, basically you calculated this and a result important on its own. Okay, let's see what we do with that. Basically, we'll obtain something very similar from a completely, absolutely different approach, and we'll study what's going on here. Sorry about that noise. It's only going to take 1 sec. Now, let me remind you of the discrete Gaussian free field, which is one of the most well-known systems in statistical mechanics. It is also known by any of these other names. Maybe some of you might be familiar with other naming for it. In particular, observe this one, massless free scalar bosonic field, and bosonic because, well, this word will be important in a couple of slides. But yeah, basically, this is the easiest field that physicists study in general. The definition is, well, just take a graph. This is defining any graph. And there is, in principle, 2 ways to define it. One is more intuitive, which is this one, via the density function, in which basically is going to be the Gaussian vector, whose density function is proportional to this exponential. So basically, this is the Dirichlet energy, which is summing the gradients squared. So what this is doing is it's penalizing large gradients. So basically, I want the heights, we can think about the value in each point as a height. I want those heights to be close together, right? So basically, there will be, like, the conditional distribution is sort of a Gaussian, yeah? So given this point over here and actually all the surroundings, this will behave as sort of a Gaussian centered at that mean value, yeah? So if this point is over here, this point will never be very down or very up. It will be something close, yeah? In one dimension, this is the Brownian bridge, by the way. So this is a generalization to many dimensions. And maybe less intuitive, but more convenient for calculations, this is another way to define it via the covariance function. So we can just define it as a Gaussian field whose mean is 0, and the covariance function is given by this function over here, which is none other than the discrete Green's function in the sets that we're working on. And in particular, remember, because this will be important, that the Green's function, by definition, is just the inverse of the Laplacian or minus Laplacian, this matter of normalizations convention. So yeah, it's just this field. You find that these 2 definitions are equivalent. And in particular, this one is a bit easier to calculate with and so on. So yeah, that's a system. And in particular, we can study function of it. Why not? People have studied the gradient of the DGFF. And in particular, we'll study the square of the gradient. So basically the norm, this square. Why? We'll see. Just give me one more slide. But for the moment, just bear with me. In principle, of course, I mean, we'll study the gradient squared and we'll take the limit as well. But remember that I mean, we can as well take the limit in the DGFF to the continuum and converge to something that is called a continuum Gaussian free field. And it is point-wisely very ill-defined because everything diverges whenever you take any sensible limit, but it's well-defined in terms of as a distribution. Yeah. However, if we are planning, so if this is a distribution, then this is even more, so to speak, a distribution, like with an even more negative index in the folder spaces. But in particular, what we can never do is to multiply, at least in the usual sense, is to multiply to distribution. So we can never take the square because that's ill-defined and you need some way around to work with that. So basically, what we will do is, okay, let's define this in the discrete case and then take a limit. So we'll take exactly the same setting as before, as in the case of Durham, yeah? And we will define, well, exactly this, just the gradient squared, and, well, this is sum over all directions, so basically this is the norm, yeah? And these two columns here is, again, the recentering. We will always be interested in recentering things because otherwise, since this is... basically, this is always positive, right? So things will blow up if we don't recenter things. So this is our definition. None other than the norm, the square norm of the grad GFF. Okay. Using some Feynman diagrams techniques, and yeah, basically is a playground for multiplication of Gaussian variables. One of the results that we obtain is this one over here. So take the cumulants again of the same field, or our new field that we just defined, rescale it appropriately. Now this does work for d dimensions in general, any d, and you obtain something like this. And before you look at it in more detail, I will save you some time and put the two together. So basically what Durham obtained in the height one field of the ASM is this one over here. And what we obtain is almost exactly, if you look like from here to the right, is exactly the same thing. Absolutely no difference. So there is a difference, however, over here. And there's a reason why I highlighted this in red. So first of all, I mean, it's quite surprising that with such a non-trivial structure for cumulants or moments, which basically define the whole field, well, in the limit, it's not defined the field, but whatever. At least with such a convoluted and non-trivial structure of the limiting cumulants, it is very strange at first, at least, to observe this phenomenon, basically, because this is coming from two completely different systems. Well, I didn't mention this one because it's not important for our work, but we also have the same conformal covariance property. But what to do with this minus sign? Because this is a minus sign. This is not minus c to the k. If this were the case, then by defining minus h, we are done. And that's it. And it's just just take the negative of the field. So it's pretty much the same. So it's a constant times the field. But this minus is not raised to the power of k. So basically, if you go to the expression of the moments and you calculate the moments, you will see that that minus messes everything up. And this field with the minus or with the plus here, these cumulants give a completely different moment structure. So this minus is a big deal. This minus one over here, so basically the 1/2 remaining, is also non-trivial in the sense that will interfere not just by multiplying this by 1/2, but in a more convoluted way. But there is a way around that. The most important thing, at least for us, is this minus over here. And that's basically the thing that struck us at the beginning and why we started to study this. Okay, mystery over here, let's put it aside and let's study fermions. if you are familiar with physics, this is somehow trivial. If you're not, this is completely new, but the only thing that we need for now is to know that there are some objects. Basically, there's an algebra called the Grassmann algebra, which satisfy this anti-commutativity property. So if, like, for more details about this, you can go to your favorite algebra practitioner and ask him or her about this stuff, but this is completely well defined. There's nothing, nothing mysterious about this. I mean, it's quite unfamiliar for most of us maybe, but in general, this is completely well defined. In particular, we can observe that these objects satisfy this very trivial property. So any power of it is going to be 0. In particular, any function of a fermionic variable is nothing else than a plus b, so a linear, right? Nothing else. Because anything of larger powers, it will yield 0, at least anything analytic. So since we cannot do this, and basically our approach here is to take eventually squares, as we did with the grad GFF square. Okay, we need a way to multiply basically 2 variables at the same spot, right? So what we'll do, and because we need things to be local. So what we will define is a pair of them, psi and psi bar. So for each side I have 2 variables, and I can do this, of course, which will be minus this. So again, these are all elements from an algebra, and we can, of course, take derivatives and integrals as well, which behave in a very straightforward and simplistic manner. Basically, an integral is the same as a derivative in this setting, in fermionic variables. So these things, I mean, doing some gymnastics of Grassmannian calculus is absolutely not difficult to show results like the one that I will give you now, because basically, right now, we only care about being interested, being able to compute things. In particular, integrating things with respect to a Gaussian measure. Yes. So in particular, we can define the so-called fermionic version of the GFF. So before we had the bosonic one. Yes. Nobody calls it bosonic unless you have to distinguish it from the fermionic one, which is none other than, well, pretty much the same thing. Just take the exponential, but now with the corresponding fermionic variables. This is just a normalization. So this is a definition. Basically, we define it in terms of how this measure acts on, like, the state given by f is given by, okay, take this f. F can be, I don't know, say this, for example, whatever, and integrate it by multiplying by this exponential. Okay, how do you even calculate that? Well, there is this theorem, which is a mouthful. It looks like complicated just because of formality. I wrote it down completely, but the only thing that this tells you is basically, okay, first of all, suppose that this is not here. So what you obtain is that if you integrate the exponential of this quadratic form over here, you obtain a determinant. Because this will be 0, 1 actually. If this set, basically if r is equal to 0, this doesn't show up, and you obtain all the determinants. Compare in particular, if this were a bosonic integral, so basically just a Gaussian integral of you're used to, what it will obtain is actually this over here. So the determinant goes down, and with the square root, but that square root you can do without, again, doing some modification. It's not important. But in particular, it's important that it goes below. Okay, and what happens if I actually do multiply by some pairs here? Well, what I obtain is basically just restrict yourself to the matrix, the inverse actually, in the rows and columns given by I and J. Yeah. So I basically these are the indexes. I don't know if I multiply by psi1 bar. Okay, I will be the row 1. So it's just taking a submatrix of A of the inverse of A and calculating its determinant. In particular, if you do this same computation but with bosons, what you obtain is, instead of this, you obtain the permanent of the same thing. So there are some comparisons, like here you obtain determinant, and then in the bosonic case, permanence. So there's a sign of a difference. And then this result is only like, basically I can do any linear transformation given by C and B, and okay, we can work it out, and you obtain this. And this will be in particular important because we'll work with gradients. And in the discrete setting, a gradient is none other than a linear transformation, right? Because it's just multiplying by a matrix given by 1 in some point, -1 in some other, and zeros all over the place. That's a gradient in the discrete setting. So that's why we need this result over here. Okay. Well, let's take again the Fermionic square gradient of the Fermionic GFF, which in this case, again, I cannot do simply this. Okay, I take this one and its conjugate, and let's see what happens. So these are sort of our field of the atoms. And we can define, okay, just a new field X given by taking this, just summing up all these squares in all the directions. Yeah. Okay. So we know how to do computations now in the fermionic setting, thanks to the Wick theorem that we saw in the last slide. Well, let's do the computations then. And we can do that exactly and take the same limit as before. You can do this in the discrete setting. Nobody forces you to take the limit, but in particular, if you do take the limit, you obtain finally this expression over here. So if you remember, okay, I'm not copying it again, but this is exactly the same thing as we saw before. And in particular, this is minus C. Okay, before I had minus C to the k, now I have a C prime to the k. Yeah, basically defining C prime equal to 1 over D. So I obtain something exactly the same thing. I mean, C or 1 over D is exactly the same, right? Because it's just a renormal, like multiplying the field by a constant. So that's not important. But in particular, what is important is that I obtain exactly this minus sign. So, okay, we won, so to speak, we did it. But why? I mean, how on earth does it happen that these two completely unrelated, in principle, systems have such a similar cumulants in these particular limits? Okay. So until now, I have explained the ASM. I've explained the GFF and its fermionic counterpart. And now I have to introduce the third system that I told you about at the beginning. And this is the one that will basically tie loose ends and shed some light on what's going on here. What is a uniform spanning tree model? Well, just literally taking a uniform spanning tree on a graph in a uniform way, none other than that. So spanning tree, just in case, it's a graph that has no cycles and connected, and it goes through every single point, something like this. Okay, so the measure is uniform. This system has been studied absolutely, like there are tons of results about this, so it's pretty much very well understood. I will still give yet one more result about that, by the end of this presentation. So there are two important well-known results that we know of in the USC. First of all is the matrix 3 theorem, or also the Kirchhoff law or whatever. basically it counts the number of spanning trees of a graph, and it's given by the determinant of none other than the discrete Laplacian. So a very straightforward relationship. So in particular, that means that the probability of this will be given by this, the inverse of the determinant, right? And now you can define a transfer current matrix, yeah, which is none other than the double gradient. So that when I say double, sorry, this I should have clarified it earlier, but the first one acts in the first argument and the second one in the second argument. And if you observe this, coincidentally, this is the discrete version of the things that we see all the time in our expressions, yeah, because, well, basically this is what will show up and what we will take the limit of later on. But yeah, this is a matrix that we can just define it. And there's another theorem, again, this is standard UST techniques, nothing absolutely obscure here, that tells you that if you want to calculate the probability of having this on this and this edge on the uniform spanning on a spanning tree sampled randomly, well, you just take the determinant of a submatrix of this n over here, nothing else. So in particular, when the probability of this edge, well, you just take, well, determinant is only that element. So you go and take that element of it there, and that's it. So this gives you a very straightforward way to calculate things. So, lesson so far. We just saw that the probability of having some edges in the UST is given by some determinant of n, so related to that. But we also saw before in the Week's theorem, a couple of slides ago, that if you want to calculate basically the mean value of some fermions, where fermions are, I mean, like just a function f, that is also related to some determinant of, well, it was before actually that a that I told you that was in the exponents, right? It was basically something like this. And then I told you that you obtain something like determinant of a to the minus 1, yeah? So basically, if now we introduce delta as that a, delta to the minus 1 is g, which is a Green's function. So all this goes to show that we know this, and we also know that taking mean values of fermions is related to taking determinants of the Green's function. Yeah, because it's literally none other than looking at Week's theorem a couple of slides ago and identifying this with this, this with this, that with that. This matrix goes here and so on. So we have a very straightforward recipe to calculate these things. And in particular, we also, you remember, maybe I should go 1 second here. You remember I told you about this second part of the theorem in which I can take any linear transformation. So this, okay, will not be proving this, but you can work this out. And if you want, instead of taking psi and psi bar, you actually want delta psi and delta psi bar, which are the elements I will use. Well, here you will obtain something like double gradient of g, or of a to the minus 1 in that case. So the only thing that I want to say here is, okay, here we have the determinant of m. Remember that m is double gradient of g. Okay, but here we also have the same thing, right? Because it's just a linear transformation of some other function of fermions, but it is also related to a determinant of m. So we only have to join these two things and identifying a probability of some edges in the USC with some fermionic mean value. And this is what this theorem shows us in a very neat way, so to speak. So with this, basically just looking at well-known results and identifying things with each other. And then, well, here we do require some inclusion, exclusion, and yeah, combinatorics. We obtain a result which tells you if you want the edges in F and you do not want the edges in G, okay, take the mean value, the Fermionic one, of what? Well, add as many of these atoms, so to speak, the zeta, as edges you have here. And whenever you do not want an edge, basically in G, what you multiply is 1 minus that zeta, right? So you want F, okay, multiply by zeta in F. You do not want G, okay, multiply by 1 minus zeta of G. That's the cooking recipe that you have here. So basically, this allows you to calculate one probability in one system in terms of the mean value of a completely different system, right? So yeah, this is the recipe that I was telling you about. Okay, and now we finally have all the ingredients, but because basically we identified these two, like the ASM. Sorry, now we have to identify the USC with the Abelian sandpile. And for that, well, one of the things that people have studied, and this was studied already in the very first paper ever for the ASM by Durham in the 1990s. One of the main results is that there is a one-to-one correspondence between recurrent configurations of the ASM and USTs. Yeah, so given a uniform spanning tree, I can give you a configuration that will happen for the Abelian sandpile in the recurrent case, and the opposite also holds. So there's a very straightforward algorithm to identify those two. So with that in mind, there is this result which I'm just writing it down for the sake of formality, but what this tells me actually is that if you want to calculate the moments, well, this is none other than probability of, since this is an indicator function, right? So expectation of indicator is probability of the events, yeah? So probability of having height equal to 1 in this and that point, given by, sorry, by V, is related to the probability, and this is a convoluted way to talk about the probability of having degree 1 in a UST. So probability of height 1 is related to, this is a different measure of probability of having degree 1 in the USC, right? So two completely different systems. One is the USC, the other one is the ASM. One probability is equal to constant times the other probability, right? So in particular, we noticed that whenever we were talking about this, taking expectations, so basically the joint cumula, the joint moments, which again is the same as talking about the joint cumulants, you were actually talking about probabilities of having degree 1 in the USC. So, okay, let's use that information and calculate things in terms of the USC. Because we also know how to work with the USC, because we know that, yeah, you can't just do calculations with the fermions. And that's the way that everything gets related to each other. And this is basically what will tell us this next theorem. So before we had defined X, which is just the sum of the zetas, and now I define Y as a product of 1 minus zeta. And the reason for this is because if you're going to talk about this, remember that now what it means is degree 1, yeah. And degree 1, well, thinking about combinatorics a little bit, is like saying, okay, I want this and not this and not this and not this, or I want this and not this and not this and not this. I'm basically playing around with that. That's the reason why you obtain this y over here. Yeah, because you do need to specify that you do not want this or that edge. Yeah. So we have a very simple, straightforward expression to calculate the things that Durham was calculating for the ASM. But now in terms of fermions. And finally, we are understanding exactly where all of this comes from, right? And in particular, once you understand things, you can compute. And okay, basically what we did is, okay, let's actually roll up our sleeves and calculate the cumulants in the limit of this x and y, again, with the same scaling as before and in the same limit, right? So remember that before we had done it for x. Okay, now we do it for x times y, which is substantially more complicated because for the discrete, like without taking the limit, okay, it's fine. It's just going to be a convoluted expression in terms of sums and products. But if you want to obtain this reduced form, basically you have to go to the limit and you need a lot of cancellations. If I have time or somebody is interested, I have a sketch of the proof at the end. But if I don't, basically, yeah, you need to cancel a lot of things in order to obtain this result over here and these permutations on points. But the point is that you can do it. It's just a matter of, yeah, choosing the right lattices, basically just, okay, at least in this case, it's only for the square lattice, right? But we are doing this for d dimensions. So in particular, this nothing is just a constant, which is, yeah, literally just a constant given by values which are known, tabulated in, you can go to some books and look them up. And if d equals to 2, I'm sorry, Pablo, I know that you told me I should have done it and I forgot. I should have written that C2 is equal to that C that Durham had calculated in 2009, which in particular is 2 over pi minus, well, whatever, but it's that. And believe me, this calculation gives you that result, which was yeah, the critical moment. But okay, in particular, well, I mean, all this also holds for d dimensions, right? So the Durham's proof was very reliant on the fact that he was working in 2 dimensions. Okay, this works for d. And okay, well, now we are greedy and we can keep going. Because much in the way that we said, okay, this is in the end just talking about the probability of having degree 1 in the UST. Okay, we can define also basically larger degrees. So you can define x to the k, yeah? So if k is equal to 1, this x is the x that we had before. But if k is equal to 2, for example, this is like saying, okay, give me, so this is going to be like products of 2 elements, yeah, 2 factors. So it's like, give me this and this, or this and this, or this and this, and this is none other than saying, give me degree 2. Yeah. So basically, in particular, if x is equal to 1, without multiplying by y, because y, what it does is it tells you, okay, do not include anything else. So x times y is telling you exactly degree 1, whereas x is telling you degree 1 or more. Yeah. And then if you look at how the degree variable is defined, the degree is none other than a sum of the indicator functions. So you might as well just say, okay, well, actually, remember back before that I had calculated like this result in the limit, which was 1 over d to the k, whatever. Well, this was actually just calculating the joint moments of the degree field. And then again, you can go even further. Okay, now I want the expectation of having basically defining these delta variables over here. what you can actually compute is the PMF, yeah, the probability mass function of having degree K1 in point 1, degree K2 in point K2, degree Kn in point Kn, in a very general setting. And it's given by, well, this thing over here. Take x now raised to the k, where each k might be in principle different, and multiply by y, so that you make sure that you're only taking that degree and no more. So it's none other than expanding a little bit on the results that we had before. And again, you can do these calculations now for a more general k. And also, we also notice that, and I will give both results in the same, so basically the most general possible result. We also notice that in the limit, you do need a lot of cancellations, and the lattice that you work on is very important. So in the discrete case, without taking the limit, most results hold for any graph. But in the limit, it's very important that you obtain a lot of cancellations, and those only happen in very, very few lattices with a lot of symmetry. And in particular, it is ZD for D dimensions, and in 2 dimensions, only the triangular and the hexagonal one. I'm not writing the hexagonal one because it's a bit more convoluted to prove, and we didn't technically prove it, but it can be done anyway. So yeah, in principle, L will be any of those lattices, and you obtain a result which is similar, the same spirit as before, but now it has a more general constant, which is given by, well, more general things, but in particular, like, see that this depends on k. If you plug in k equals to 1 in every single case, of course, it will recover the thing before. And yeah, this works for ZD as well as for the triangular lattice and the hexagonal one. And this sort of points towards a potential universality property, because at the end of the day, the only thing that changes here, if you change the lattice, is a constant. But a constant you can do without, basically just by redefining the field. But the cumulants or the moment structure in the limit is the same one. But yeah, I think I don't have any more time to give you a sketch of the proof. If you're interested, please let me know, but otherwise, I think that's it. Thank you very much.
Okay, so we have questions from the audience.
I have a question.
Pablo?
Alan, so do you have a coupling between sandpile configuration and spanning tree configuration, or it's just the probability of having a
If we have coupling, in which sense?
Yeah, in the sense that you have a function between each configuration of the spanning tree, each spanning tree with each final configuration of the sandpile.
So to each, if you give me one spanning tree of a graph, I can give you to which sandpile configuration it corresponds to, and the other way around. There's a bijection.
Okay.
Not for only for the allowed configurations, which are the recurrent ones. Not everything will be allowed in the recurrent state of the Markov chain.
So the result would be a consequence of that, the relation, right?
Sorry?
The result of the probability result, that you have the probability that the degree 1 in the spanning tree is the same as up to 1 particle in the sandpile.
Yes, Yeah, I mean, so once you have this identification between this correspondence between UST and ASM configurations, then you can, I mean, one thing that is true is that if you have height 1, then it will be a leaf in the USC, but the converse is not true. You can have a leaf, and not necessarily the height will be 1, but you are able to mix to calculate to relate the probabilities of having on the one hand height 1 and on the other degree 1. So in particular, probability of height 1 is equal to 1 over 2d times probability of degree 1. So it's not the same, but it's related by this concept.
Okay.
This is what, I mean, summing up this theorem in a more straightforward way, that's what it tells you.
Okay, thank you.
So maybe I have a question. Maybe this is related to Pablo's question. You're not able to, this description doesn't give you the other heights,
No.
the other height fields.
Very, very important to highlight that. It is not true. There's no straightforward relationship between having height 2 or 3 or whatever and degree 2, 3, 4. There is a relationship, but it's way more convoluted. Basically, it tells you that probabilities of having other heights are related to events which are non-local, in the sense that I don't remember exactly the expression. This can be looked up in many papers, but it's like count. You have to count how many. So if you're talking about this point, you have to count how many of its neighbors are antecessors, and by that, what is meant is, so this will be an antecessor if the spanning tree basically does something like this, whatever, and then goes through this point before going to the root. And that, but you can see that this point can be an antecessor of this one and go very far away and then come back. So it's a highly non-local, at least in this sense, non-local property. So it is very, very difficult to study higher heights. People in general, yeah, I mean, it increases exponentially the difficulty.
Okay.
There are some things done as well with clusters, expansions, and so on, but yeah, as far as I know, there's nothing that straightforward that we can apply.
Okay, so I have a question. So the first thing is that in a sense that the Abelian sandpile is different to the models in the sense that there is a very natural dynamics associated to the Abelian sandpile. I mean, it's a dynamic that is also the invariant measure of the Abelian sandpile is the invariant measure of something, no? Of the process itself, but the other models don't really come with the natural dynamics, right?
Right. Yeah. In some sense, it's like, okay, sampling something. Okay. Well, but in this case, you can think about like, okay, sampling one configuration of the DGFF doesn't have any, or UST, it doesn't have any dynamics, but you can just sample it. Well, in much the same way, once you obtain the recurrent state of the Markov chain, you can just sample one configuration of the ASM. So even though the algorithm keeps on going, the system as a dynamical system, you can think about that as just sampling one configuration of those recurrent ones. Yeah, I don't know if that answers your question.
A different one. So it's so related. No, in the continuous model, there is a natural way to introduce a dynamics, which is that you just do for example, so there are these stochastic PDEs that have this these Gaussian processes as invariant measures, right? So, but it's kind of it's not clear to me that those dynamics has something to do with the Abelian sandpile. So do you know if there is a way to study to look at the scaling limit of the dynamics of the sandpile, and not only at the invariant measure of the sandpile?
As far as I know, I've never seen anything pointing in that direction. Basically, you mean like obtaining an SPDE related to it? I mean, there are some modifications of the sandpile, which are like the divisible sandpile, in which case basically the height is a continuum variable. But I don't even know which kind of limit you would have to look at in order to study something like that if you leave the system as it is, because the divisible one, I understand that it has different properties. So I'm not sure what kind of limit you would have to look at. I haven't seen anything like that, but I should ask Violeta probably, or Alessandra.
Hey, Alan. Sorry, it's Leandro here.
Okay. Hey, Leandro.
So Newton, the problem with this kind of system is usually because you have correlations that are very, very strong. So it makes the process difficult to analyze on the dynamics. And like for us, it's really saving the data that somehow we can extract like a UST from it. But those models, you really need to go through a trick. I don't know any results of, say, hydrodynamic limit for the dynamics. So I think there's perhaps something for like where your dynamics is putting a single particle at the center and then evolving just by always putting the particle at the center. But in this version that we're looking at, which is to put particles at random points, I think the correlations become too strong for the current methods.
Yeah, but I mean, even at the physicist level, I mean, or the heuristic level, I don't. I would like to understand what could be the at least a candidate for limit, no?
I mean, there are conjectures, for example, and not coincidentally, I wrote down at the beginning that, sorry. Over here, give me 1 second. That this action was proposed as a system that actually, in this limit that we're talking about, emulates the height one. In some sense, our results do back it up because, okay, we didn't study any limiting field, but we did study the limiting cumulants. So this is a candidate, but only for the height one. Now, if you want to study the whole theory, like the height one would be like some, I need to be careful with what I'm saying because don't know that much about CFT, but if you, as far as I understand, basically proving that this converges to some CFT means, okay, the whole system, the whole Abelian sandpile converges to it, and in particular, every single observable converges to one in a CFT, but height one is only one observable. So people do conjecture still that this should converge to a particular CFT, which is a log CFT because of the correlations, this name, with a central charge given by this. And in particular, this theory is such a theory. But you have to do it for every single observable. There are many calculations in a physicist way that have been done about the ASM that do back up the this conjecture. So not only the correlations in the height one, but also like, yeah, some approximations as well in different heights and so on. And they do seem to match those that you would obtain in a CFT. But so far it hasn't been identified. But
Okay,
this,
thank you.
yeah, this is different to hydrodynamic limits.
So, any other question? So, if not, let's thank Alan again for his talk.
Thanks to you for the space.
So next week it's Workers' Day everywhere in most places. So there won't be seminar next week, but so we meet again on in 2 weeks from now.
Okay.
Gracias, Ana.
Gracias a todos. Thank you very much, everybody. Well, hope you find it interesting and see you soon.
Ahora, gracias.
Chao,
Bye.
muchas gracias.
Chao a todos.
Nos vemos.
Se pasa.